12. We're just missing 3 folks. We'll go ahead and get started here this morning. So, hello. All right, let me get over here to Buzz on the screen, get our course up here. Somehow a fake student earned a star. I got a star on the screen for this class. Of course, Algebra 3 0B. I don't know where the star came from. Let me click on the star, see what it tells me. I got a badge. Yay. I don't know why. I don't know anything about the badges. All right, let's go back to the classes here. 0B, Algebra 3. Let's take a look. All right, so if we go to our grade screen, so you should be done with the tests. We are completely finished with Module 5 now. So if there's anything you're missing from Module 5, don't delay. Don't wait till you forget it all. Get it done. Get it turned in soon. All right, don't wait till you forget all of it. Everything should be done. We are starting the first 2 lessons of conic sections. We're going to do introduction to conics. We're doing parabolas and ellipses. Then we're going to move on to this next week. And this is a very short unit. You see, we're going to have the exam in just a couple of weeks. So, intro to conics and parabolas. All right, let's go back to our activity screen. And let's look at our lesson on intro to conics. The parabolas lesson. We're familiar with parabolas, but we're going to look at it a little different way. So the Greeks actually discovered conic sections during the classical period, which is 600 BC to 300 BC. So a long time ago, not quite 3,000 years ago, and mainly considered their geometric properties. So in the 17th century, which is a long time after that, like 2,000 years later, mathematicians developed more applications for conics, and conics played a crucial role in the early development of calculus. So conics have played a big role in math. So what is a conic? A conic section is the intersection of a plane and a double-napped cone. This is what a double-napped cone is. Imagine taking 2 ice cream cones, turning them tip to tip, and putting them together. You know, like stack one on top of the other. Yeah, it can be really good to balance the tip on top of the tip, but that's a double-napped cone. And then a plane is just like a sheet of paper. Like you take a sheet of paper and, you know, if you could pass through the cone without busting it. So you'll see a diagram over here. So I got a different little illustration of that right over here. Let's make this full screen. So this is a double-napped cone. You can see the blue plane that intersects it. And see right there, if it just slide it through just like that, notice it makes a circle. It can make it a bigger circle or a small circle depending on where on there that we do that. Now there's just a point right there in the very, very center. But if we move this plane, I'll hit the start button. See, now that becomes a much different shape as it goes up and down. I stop it. Oop. When I stop it, it quits. It goes back to where it started. All right. Well, I'll just play with the rotation myself. It's not being nice. Oh, there. Oh, we can look at it this way. I can change the way we look at it. But watch it as it moves. It'll become more of an oval, an ellipse, and then it'll become a parabola when it gets past the end. See, now it's more of a parabola right there. And then as it goes more up and down, now it's a hyperbola. So as you take that plane and move it around, and we can raise that, look at it in different directions. But you see how the shape changes. So from a circle to an ellipse to a parabola to a hyperbola when there's 2 of them. That's just kind of a nice visual of what we're talking about. Now back to a circle when it's flat. But it just sits there and rotates back and forth. Oh, there's where the little pause button right there. So it just creates a parabola. Now, when it gets up here to where it actually intersects the top one is when it starts creating a hyperbola. See, that's a hyperbola. And we'll look at all of this. So just a little illustration of conic sections. Courtesy GeoGebra is a pretty good site. They have lots of good graphics and visuals that you can look at on GeoGebra. But there it is, just in a drawing illustration. Circle, an ellipse, a parabola, or a hyperbola. That's top and bottom. Notice none of these intersections go through the vertex of the cone. So this is all just using the different sections of the double napped cone. So, all right, so we got some different vocabulary we're going to use. So there's something called the locus. And no, we're not talking about that insect that makes a lot of noise and goes, eh. No, that has a T on the end. That's a locust. This is just a locus. So in this course, although we recognize conics are produced with the intersection of a cone and a plane, we'll study them as a collection or a locus of points that satisfy a geometric property. So this will permit each of them to be described using an algebraic equation. So recall that we can describe a circle as this: x minus h squared plus y minus k squared equals r squared. Or if it's just based on the origin, it'd be x squared plus y squared equals r squared. Right? The h and k moves the center of the circle off of the origin if you graphed it. So this is just allowing for every circle. But it's the x squared plus y squared equals r squared with the ability to move it off of there. So we have the equation for that. And that h and k are the offsets from the origin, where the point hk would be the center of the circle instead of 0, 0. That's what the h and the k are. H minus k. And of course, r is the radius of the circle. So if h and k are 0, the circle's centered at the origin with the radius r. Now, parabola, we're going to get some more words here. A parabola is the set of all points. See, I mean, we've used parabolas a lot in quadratic equations, but haven't really talked about what a parabola is. All points that are equidistant from a fixed line. There's a line called the directrix. And if we draw that line, all the points of a parabola would be the same distance. And a fixed point focus that is not on the line. So you have a focus and a directrix, and all the points would be the same distance from that. So the vertex of a parabola is the midpoint between the focus and the directrix. The axis of a parabola is a line that passes through the focus and the vertex. And we know what a vertex is. That's that center point of the parabola. That it kind of mirrors both directions from that. We call that the axis of symmetry also. When we just talk about the axis of parabola, we talk about the axis of symmetry. So we can use the definition of parabola to derive an equation in standard form for a parabola. So let's look at this directrix first. I'm going to look at this in GeoGebra. So let's see. I didn't look this one up ahead of time. GeoGebra directrix and focus of a parabola. There we go. Let's look at this one right here. First one's probably pretty good. All right, perfect. This is exactly the illustration I was looking for. All right, so with this parabola, and we see the nice blue parabola drawn there, this has a focus that's labeled as F right there. And the directrix line for this parabola is at y equals negative 2.4. Now notice point A on the parabola is exactly 6.48 from the focus and 6.48 from the directrix line. But we defined a parabola as a set of points that are all the same distance from those 2 points. So if we move this A, look how it stays the same distance from both the focus and the directrix, no matter where it is on the parabola. And it said that the vertex is exactly in the middle. See, it's 1.4. It crosses the y inner axis at negative 1. So the focus is 1.4 above the vertex. The line, the directrix line, is negative 2.4. It's 1.4 below it. But every point, as you can continue on, every point is the exact same distance away. So that's how a parabola is defined. There's actually logic to a parabola. We just know it's that shape that's created by a quadratic equation, but it is defined mathematically as the set of all points. Now this is, we can move things. If we move it over, doesn't matter there. Let's see, if we change the P, that makes it a wider or skinnier. Oh, look, if we go upside down, now the directrix line is above it and the focus is below it. Oh, let me grab that point. But see, it's still the same distance. I didn't mean to move that. Still the same distance from either way. Even if it's an upside down parabola, the directrix line's above it. The focus is always inside the parabola. See, when it's really wide, when it's really wide, it just moves the focus and directrix farther away. See, now it's 4.2 away, but it's the same both directions. So, nice illustration of that from GeoGebra. Thank you, GeoGebra. But it has it in our text as well. Now, we have this equation right here. So, let's see. We're going to write this down. This would be good to have in your notes. X minus h squared equals 4p. You're like, oh, we got another variable in there, this p. And p cannot be equal to 0. And there's two versions of this, or there's also a y equals for a parabola. 1 over 4p x minus h squared plus k. And again, p cannot equal 0. All right, I'll put that up on the screen in a minute. But yeah, let me open that up. So notice there's an x minus h squared in there. And that would make sense because we know the equation here. I'm going to go ahead and put it on the screen this way so I can point to things and talk about it differently here. Turn on our light. See, notice there's an x minus h and it's squared. Well, we know anytime that we're graphing a parabola, it's because it's a quadratic equation with an x squared. So this would create an x squared. Now, if you notice, this looks very similar to the vertex form, where the vertex is at hk, right? This is the vertex form. We're just adding some other parameters to figure out 1 over 4p. P is that distance between the focus and the vertex, or the vertex and the directrix. But there's a way to calculate that coefficient that's out front. But this is another way to write that same equation. X minus h squared equals 4p over y minus k. And both of these, p cannot be 0. But if we look back at that illustration we had on that, see the p equals 4.2. That's that distance between the vertex and the focus, or the vertex and the line of directrix. See, 4.2, that's the p. So when we have this p in this equation, that's talking about that distance between the focus and the vertex. 1 over 4p is another way to do that. Starting with this equation, we can rearrange it and get y equals, and that's how you get this part of the equation. So, all right. Of course, if the vertex is at the origin, then your h and k are both 0. So it's x squared equals 4py, right? If this is 0 and this is 0, it's just x squared equals 4py. Or y equals 1 over 4p x squared, because the h and the k would be 0 in that case, if the vertex is at the origin. All right, so the standard form of a horizontal parabola. The horizontal is one that goes sideways, right? Because we usually see up and down. We see parabolas go up, we see parabolas go down. We don't normally see ones that are sideways. But since we're defining it, it's the exact same equation. You just switch the x and the y. Now it's y minus k and x minus h over here. You're switching those two things. Notice it looks a lot like this one, but we're just switching the y minus k and the x minus h, trading places. So this is vertical. Vertical. So for horizontal, we can put that in our notes. That's the y minus k squared equals 4p x minus h. And again, p cannot equal 0. You just swap places with those two. But yeah, the y is squared in a horizontal parabola. And there's the same equation underneath it if you have x equals instead of y equals, x equals form. So it's good to have those in your notes. All right. So it says an example. We put the parabola in the standard form by completing the square of the general quadratic. Oh, do you remember completing the square? Maybe we should work through that. Let me write that problem down. That's the standard form equation where you list everything on the same side. Instead of equal to 0, x squared plus 4x minus 8y minus 20. So if we do completing the square, which we don't do a whole lot, so that's why I'm reviewing this, we move the y's to the other side. So add 8y, add 20. 8y plus 20. So that rearranges our equation to be x squared plus 4x equals 8y plus 20. And we're wanting to complete this to where it will be a square trinomial, perfect square trinomial. And the way we do that is we take that middle term, which is 4, and we divide it by 2. And then we square that. So 4 divided by 2 is 2, and then we square 2. So we add 4. But we can't do that to this side without doing it this side, or we've changed our equation. So now we know this is a perfect square trinomial that is x plus 2 squared equals 8y plus 24. All right, and if we want it to look like this, we factor out what we can in front. X plus 2 squared equals 8y plus 3. All right, so now it looks like this form, 4p. P must be 2 because we got 8 as our coefficient, and that has 4p as our standard form. So p equals 2, since 8 equals 4p. Divide both sides by 4, p equals 2. But yeah, we completed the square. We made this a perfect square trinomial. So it's x plus 2 times x plus 2, which would be that. And we can create that equation. Let's see what they did here. Yeah, they added the 4, and then they pulled out the 8. See, now that's in the vertex form. So the vertex is at -2, -3, because it's x minus h, y minus k. So we could actually graph that just from this equation now. We put the vertex at -2, -3, and we would make that focus line at 2 above the vertex, right? Because we know P is 2. So that focus point is 2 above the vertex, and the directrix line would be exactly 2 below the vertex. So P is positive, so it opens upward. Focus is 2 units up, so it'd be at -2, -1. And since it's vertical, x equals -2 is the axis of symmetry that goes up and down between it. And the directrix is perpendicular at y equals -5. So more practice there. So they give you a practice problem right here. Focus and directrix of the parabola x squared minus 8y. So it says find the focus and directrix of that. So I'll leave that one where you can do that, because you can click here and check your answers and make sure that's working. Yeah, gives you the answers right there. So there's a practice problem built into our lesson where you can practice and make sure that you can find that. All right, so here's another example. Notice this is one of those lessons that's just all on one page, all on one page, one of one. This unit is one that we have borrowed from pre-calculus. Because remember, Algebra 3 is a course that Arkansas does and a lot of other states don't. So we put together all the topics that are in Algebra 3. This is one of the topics. And so we steal those lessons from other courses. And this one comes, and so the pre-calculus lessons are all on one page here. All right, so where were we? Right here. All right, we could also write the equation of a parabola if we're given information. So let's write the equation of a parabola whose focus is -4, 0, and the directrix line is x equals 8. Okay, so I'm going to write this down. Okay, so what do we know about this? If we we kind of sketch this, I don't think I have any graph paper right now. I need to print some more graph paper out. We'll just kind of sketch this. X equals 8. Well, that's an up and down line way over here, right? So if we have the directrix line where X equals 8, and the focus is at -4, 1, 2, 3, -4, 0. So the F is over here. So obviously we have a horizontal parabola. But the focus is over here, and this is 8, right? So 1, 2, 3, 4, 5, 6, 7. That's an 8. What is our P? Remember, P is the distance from the focus to the vertex and the vertex to the directrix. It's always going to be exactly in the middle. The vertex is going to be exactly in the middle. So if this is, how far is this? This is -4. From -4 to 8, there's a distance of 12. And we know that the vertex is exactly in the middle. So just divide that by 2. And we know the P is going to be 6. P is 6. So we can count 1, 2, 3, 4, 5, 6. Here is where the vertex of our parabola is. And if we sketch it, we know it goes this way because the focus is always in the middle of the parabola. And the directrix line is outside. So that's a nice sketch of what our parabola should look like. So let's see, if we write the equation for that, we know it's a horizontal. So y minus k squared. So what is our k? Well, the vertex is at 2, 0. HK, right? The vertex is the HK, 2, 0. So our k is 0. So our equation is going to be y squared, because our k is 0, equals 4 times p, equals p is 6. So 4 times 6 is 24. And then we need the x minus h. Oh, I'm sorry, right here. X minus h. X minus h is 2. So this is the equation for this parabola. Now let's actually graph that and see if that works correctly. So we'll go over to Desmos now. We'll use GeoGebra and Desmos today just to get out there and experiment with some math tools. All right, so if we said our equation was y squared equals 24x minus 2. Oh, it has to open left. It's a negative. We forgot that little detail. If we want it to open the other way, we've got to put a negative in front of our 24 because it opens to the left. It opens towards the negative x's. The 24x minus 2. Look there, we've got the 2, 0 is the vertex. And it does open left. Now it's wider than when I sketched it, but a sketch is just a sketch, right? It's just that, but the focus should be at -4, 0. There's the focus point, and the directrix was at x equals 8. So there, that's 6 away on both sides from the vertex. So that's exactly what it looks like. Let's compare to what they got in the lesson. Oh, they put it in the other version. Oh, it says you can write it. This can be written as either, and we wrote it as y squared equals -24x minus 2. That's exactly what we had on our paper. Or if you want to write it in the other version, x equals, right? So you divide by the -24 and then add 2. So -1/24 y squared plus 2. So you can write it in either way. Okay, so they give you another one for you to try. Write the equation of the parabola that's symmetric with respect to the y-axis. If it's symmetric to the y-axis, That means the vertex is on the y-axis. This says it has a vertex at the origin and contains the point 6, 3. Oh, that's a different one. It doesn't give you the focus. It doesn't give you the directrix. It doesn't give you P. It just tells you a point on the line. Symmetric to the y-axis. That tells you it's up and down. All right. Vertex is at the origin. Oh, we're gonna play with this one because this is a good problem. So let's see. Origin is 0, 0, it said, and contains the point 6, 3. Let's do a little sketch of it to start with. 1, 2, 3, 4, 5, 6. 1, 2, 3. So this over here is a point. It says the vertex is the origin, so it's pretty wide. And it says the y-axis, we also should be going through -6. So if this is 6, 3, we also go through -6, 3. Because it says symmetric to the y-axis. If it's symmetric to the y-axis, then it's a mirror on both sides. 6, 3, -6, 3. And it wants us to write the equation for this parabola. Wow, any thoughts on that? What would we do? How would we write an equation for that parabola? We have no idea what the P is. All we know is a point. Anyone got any suggestions? Let me see. Look over here. What do we know about it? We know it's vertical. So we know we can use this equation or this equation, right? We know the P cannot be 0, but we don't. We do know, okay, let's write the equation, what we do know. We do know the H and the K. The origin at 0, 0. So H and K are 0, right? So that simplifies the equation to x squared equals, x squared equals 4p times y. 4py. Or y equals, if we want to do a y equals 1 over 4p x squared. H and k are both 0. 1 over 4p x squared. And we know it has to contain this point. Got any ideas on that? Is that making you think? Well, if it contains that point, that this equation would have to work for that point, right? So let's see, can we make any progress by substituting? If we know the point 6, 3, then 6, 3 has to work in that equation. So if we put 6 squared equals 4p and the y is 3, 6 squared equals 12p, 6 squared is 36, 36 equals 12p, p equals 3, right? Could divide by 12. So the equation for this must be x squared equals 12y. Because 4 times p times y. If p is 3, 4 times 3 is 12, 12y. Or y equals 1 over 12x squared. Either one of those. So let's try this. Let's graph x squared equals 12y and see if it creates a parabola that goes through 6, 3. Okay, let's put our 6, 3 first up there and see if we hit that point. There's the point 6, 3. All right, and we said it's x squared equals 12y. Oh, looky there. That graphed a parabola, and it went through the point 6, 3. See how we got there? any point on that line, you should be able to substitute that point into the equation and it be true. If x squared equals 12y, that would be true for every point on that parabola. That's why that is the graph of that equation, because every x and y that's on that line should work in that equation. So we substituted that point in to find what the equation was. Let's see what they did here. Let's check your answers. Let's see how they approached it. So write the equation for the parabola that's symmetric with respect to the y-axis and all that. So the standard equation is x squared equals 4py, because we took away the h and k since it's at the origin, or the y equals 1 over 4px squared. Now, since the point 63 is on the parabola, then the ordered pair 6,3 must satisfy the equation. So 6 squared equals 4p3. That's exactly the way we did it. We substituted it into that first equation. 36 equals 12p, was able to solve for p equals 3. Now we can just replace the p in the equation and come up with x squared equals 12y, or the y equals 1 over 12 to the x squared. And the way we checked it was to graph it. We actually graphed it to check ourselves. Are we right? We knew we were right because we've already verified it by graphing it and finding out it is a parabola and it does go through the 0.63. All right. So here's a nice little table that might be nice to put in your notes that kind of help you find, how do I find the focus? How do I find the directrix? How do I find the equation? If p is greater than 0 or p is less than 0, right? So here's the description of it. If the p is greater than 0, your focus is at h plus p k. So if you know the vertex, parabolas with vertex at hk, right? So if you have the vertex and you know the p, you know the focus is going to be h plus p k, gives you the point of the focus using the vertex and the p. The directrix is going to be x equals h minus p. So that'd be the line for the directrix. And this is the equation, y minus k squared. So this is an axis of symmetry parallel to the x-axis. Both of these first two are horizontal, opening left, opening right parabolas. This one opens to the right. This one opens to the left. All right, so there's the little table that shows you how to find the focus and directrix and the equation. And here's the up and down. The p is greater than 0, it opens up. P is less than 0, it opens down. And here's how to find the focus and the directrix and the equation. All right, and it talks about parabolas in the real world. We see lots of parabolas in the real world. In fact, we're going to do a collage of this unit where you go out and find pictures from the real world and put them in a little collage. Remember making a collage back in elementary school? You get little pictures out of magazines, paste them on a poster board, made a collage. We're going to do that. We're just not going to do it with magazines. We're going to do it with the internet and a Google Doc. Kenny's living room window has the shape of a parabolic arch that's 12 feet high and 18 feet wide at the base. It says find the equation for the parabola if the vertex is put at the origin. If that was the origin. So the standard form, since this is an up and down, would be the x squared equals negative ay, where a is 4p, right? Negative 4py. They're just using a single variable for it. And we know the point 9, negative 12, since this is 18 feet wide, we know from the center, this is 9. 9, negative 12 is that point right there. So they substitute that into the equation to find negative 6.75 is equal to the 4p, or equal to the a. So the equation is x squared equals negative 6.75y. So it gives you an example of how to do that with a parabola in the real world. All right. Ignore this. You don't have an online textbook. This is our online textbook. So this is some other stuff that doesn't apply for us. Let's go to look at the assignment for the parabolas. Okay, here it gives you an equation. It wants you to find the vertex, focus, directrix, and focal width. Oh, we didn't really talk about the focal width. Let's see. Let's go back to our lesson in there. the focal width. Did we miss focal width there? Did they talk about focal width? All right, conics. Standard form, vertex. Standard vertex. Of the width of the parabola at the focus. They just called it something different. It's the absolute value of 4p. The absolute value of 4p is the focal width, the width of the parabola at the focus. So in this one that we graphed, the focus, see, since we said p equals 3, the focus point would be 3, 0. Oh, 0, 3, sorry. 0, 3. That would be the focus. And we said the p was 3. So what is the width right here, the focal width? Well, it goes from 6, 3 to negative 6, 3. So notice the width here at the focus. That would help graph it correctly if you didn't have an automatic graphing thing like this. It goes from negative 6 to positive 6. That width is 12 at the focal point, which we said the p was 3. So 4p, 4 times 3 is 12. So that is the focal width. We can see that's how wide the parabola is when it's directly even with the focal point. So yeah, I skipped that. The width of the parabola at the focus is 4p. So that's good to know. Let's add that to our notes. Focal width is the absolute value of 4p. So if this was negative, we just call it positive. Because the absolute value, we ignore negative, right? So if p was negative 3, it would still be 12. 4 times negative 3 is negative 12. Absolute value of negative 12 is positive 12. So we'll add that to our notes. And you can add this other equation as well. So, all right. So I'll go back and look at this again. Vertex, focus, directrix, focal width. So if you can find this information, the focal width will come with it. So there's the vertex, there's the focus, there's the directrix. Is that it? If this is 4py, what's p? And p will help you find these other things. Now notice all these have a vertex of 0, 0. So that's not going to help you. They're all 0, 0. But where's the focus? Where's the directrix? And what's the focal width? That's the differences. Another one, x equals 4y squared. Find those 4 things. What's the standard form of an equation of a parabola? That has a vertex at the origin, and here's the focus. So if you know the vertex and you know the focal point, that will tell you what p is, and you can come up with the equation. Find the standard form of the equation of the parabola with focus at 0, negative 9, and direction y equals 9. Okay, so they give you the directrix line this time and the focus. Right, so you can find the vertex right in between those, exactly in the middle, and figure out what p is. There's another one, focus and directrix. Oh, we got one open response right here. Here's a building that has an entry this size. Find the equation for the parabola if the vertex is at the origin. This is exactly like that last problem in the lesson, where this is a window in the front of the dude's house, right? So you can use that example if you get lost to figure out the equation. Now, yours may be a little different than this one. Remember, there's a bank of questions that it pulls from. So if you don't have this exact problem, you'll have something very similar. And by the way, if you're looking at this and you have a dark screen, I really haven't covered this in class. Some of you guys may have a dark screen instead. See, mine's white. If yours is dark, if you get out of the lesson, I'm going to get out of the assignment. I got to get out of this too. If I go back to this front screen, I'll show you how to fix it real quick. Go to your choose theme option and choose a light color scheme. It kind of does a dark screen like that. And it's hard to see some of these equations. Choose a light color scheme. And then you can choose whatever color you want for the highlights, you know. But change it to a light color scheme if you're having trouble seeing equations. And that's up here. Click on your name and choose theme. All right. So that was all the parabolas lesson. Let's look at ellipses. This is our second lesson for this week. Ellipses. All right. Let's go back to GeoGebra again here. GeoGebra ellipse. Let's see what this one shows us. Oh, wow. It gives us lots of detail here. All right. I don't know if I want to use that one or a different one. Let's use the conic. Let's see. This is graph and equation. Like I say, GeoGebra has a bunch of these. Perfect. All right. So an ellipse. Here's how we define an ellipse. An ellipse has two focal points. Two focal points, F1 and F2. And it does have a center of an ellipse. An ellipse is like an oval, right? It's a circle that's been stretched out either up and down or left and right. This one, since the focal points are on the sides of the center of the ellipse, this is going to be one that's wider than it is tall. So let's see, if I click this little button, I think it'll draw the ellipse for us. Yes, it will. An ellipse is defined as the set of all points to where if you add the distance from F1 to A and F2 to A, which A is any point on the ellipse, it will always total the same, the total distance between here and there. Notice the distance from F1 to A is 2.03, and this is 3.97. Notice the distance is 6 when I add the distance from here and from here together. As I move that around, it always is 6. Even when I go right here, look, right here, the distance is 5. 1, 2, 3, 4, 5 to that focal point. The distance is 1 from this focal point. So together they equal 6. But if I move that, it's still going to equal 6 anywhere. Exactly 3 right there. Always 6. So it's the set of all points that are the same distance away from both focus points added together. I mean, it's the same distance. You can add the distance from that point to both focal points. It's going to be the same. And we can change it. It says D equals 6. I guess it's A plus B. That's the way it defines it. The distance is A, and this is B over here. All right, so that just kind of gives us a look at it. So here it is on just a picture. I like the GeoGebra one because we can move it and we can show how that always stays 6. But the picture shows the same thing. An ellipse is the set of all points, the XY point, the sum of whose distances from the two distinct fixed points is constant. It's always the same sum, distance 1 and distance 2. The one we were looking at is 6 was the distance. And the line that passes through the two foci, focus, plural, foci, the two foci intersects the ellipse at 2 points called the vertices. Right? So there's 2 vertices. There's one that goes left and right, one that goes up and down. The longer one is called the major axis. These are the 2 axes, right? Major axis, and the shorter one is the minor axis. And the midpoint is called the center. That's where those 2 axes cross each other as well. That's the midpoint between either axis. That's the midpoint either way. So the chord perpendicular to the major axis that's there is called the minor axis. That's the one that goes the shortest distance in the ellipse. So this is a horizontal ellipse. It depends on the major axis. The longest axis, is it horizontal or is it vertical? So it says the major axis is 2a. So the distance from the center to the major axis is known as A. So it's 2a wide. It's B from the center to the minor axis, to the point on the circle. So that's 2b. And the distance between the foci, which would be from there to there where the foci are, is 2c. So let's look at the standard equation of an ellipse. I'm going to do this on a different sheet of paper. All right, so if we put this in our notes, x minus h squared over a squared. Now let's define some things. Let me kind of roughly draw. If we have our major axis and our minor axis, the center is going to be HK, right? That's the center. A is the distance from, here, let me do it like this. From on the major axis, from the center to the edge, to this major vertex. B, just to illustrate this nicely, B be this line. So the H and the K is the center of our ellipse. The A is the distance from the center to this major axis edge. B is the minor axis distance. All right, so that defines all those variables. Showing it in a nice illustration there. So you might want this in your notes, A and B and the HK, just to help you out there. I'll leave that up for a second for any of you copying that down. But that is the equation that we use right there for a horizontal ellipse. All right, let's go back here. Standard equation of ellipse. For a vertical major axis, we just switch the A and the B. Look, everything's exactly the same. So let's designate that on our notes. Horizontal, vertical. So vertical's x minus h squared over b squared plus y minus k squared over a squared equals 1. So there's the difference between the horizontal. We just switch the A and the B. So that one would be a tall one. A tall one instead of a wide one. This one's a wide one. The other one to go up and down. Okay. The foci. Here we go. The foci lie on the major axis, and they are C units from the center. And here's how it's defined. C squared equals A squared minus B squared. Okay, so this will be interesting to add to our notes. Let's see. So C squared equal A squared minus B squared. And the foci, so the foci would be, we're going to say right there, and we're going to call this C. This distance right here is C. And here's how we find C. We take A squared minus B squared, and that gives us C squared. So we take the square root of that, and that'll give us the distance of those foci. C distance from center. All right, so that's the distance, and it's always on the major axis. And you're like, man, I've always just drawn ovals. I didn't know this was so complicated. There's a math to everything, guys. There's a math to everything. So that is our distance to find the focal points, or the foci. And A squared is always bigger than B squared, because A squared is always on the major axis. Right, if it's an up and down, the A is still with the major axis. If the center is at 0, it makes it a very simple equation, right? Because with x minus h is 0, y minus k is 0. It's just x squared plus y squared over a squared plus b squared, right? X squared over a squared, y squared over b squared, and they equal 1 when you add them together. All right, so writing the equation of ellipse requires finding the values of h, k, a, and b. There's the big hint right there. You got to find h, k, a, and b. Of course, h and k is the center. That's the coordinates. So the center will always be halfway between the foci or the vertices. And recall the distances from the center to vertex are a and c, respectively, for the vertex and the focus. All right, so let's test our skills. Let's find the equation. Okay, find the equation for an ellipse vertices of 3, 0, and negative 3, 0, and foci of 2, 0, and negative 2, 0. Okay, remember the vertices are on the major axis. All right, so the vertices and the foci. So we know if we drew this, it'd be horizontal because 3, 0 would be over here, negative 3, 0 would be over here. And since we know that's the vertices, this is the major axis. Right? If it was 0, 3 and negative, or 0, negative 3, we know it'd be up and down. The foci is at 2 and negative 2. 2, 0, negative 2, 0. I didn't give myself much room in there. I drew that really small. All right, so what do we know now? We know the center must be halfway in between the vertices or halfway in between the focal points. Well, that's easy. Since this is 3 and negative 3, it must be on the origin, right? So we have an ellipse that's centered on the origin. And now we know some distances, right? It says we need to know what to write an equation. We need to know x, I'm sorry, not x, h, and k, and what else did it say we need to know? A and b. So this is what you need to know to write that, because h and k and a and b are what's in the equation. All right, so if we can find h and k. Well, h and k are zeros, right? Because that's the center. HK is the center. HK center. Put that in our notes, just to make sure we don't forget that. A is the distance from the center to the vertex. Well, the center is a 0, 0. The vertex is a 3, 0. So our A equals 3. B, we don't know this distance right here. We don't know that. But we do have a formula that says c squared equals a squared minus b squared. And we know what c equals, because c is the distance from the center to the focal point. Well, from the center to the focal point, c equals 2. Okay. Well, if we got some points, c squared, 2 squared equals a squared minus b squared. All we do is solve for b. 4 equals 9 minus b squared. Okay, let's do this. Let's move b to the other side. Let's add b squared over here, just to make it positive. B squared plus 4 equals 9. Subtract 4. B squared equals 5. So b equals the square root of 5. B equals the square root of 5. And you're like, oh man, it's going to be nasty. No, actually, it's going to be nice. We're going to like this. We're going to write the equation. They want us to write the equation for this ellipse right here. Well, it's horizontal, so we know we're using this equation. So let's write our things. X minus h. H is 0. So this is just x squared. Right? Because it's 0. X squared. Over a squared. What's a? A is 3. What's 3 squared? 9. Okay, that's the first part of our equation. Plus y squared, because k is 0, plus y squared over b squared. What's b? Square root of 5. What's the square root of 5 squared? B squared is 5. And it always equals 1. That is the equation for an ellipse that has vertices at 3, 0, and negative 3, 0, and focal points of 2, 0, and negative 2, 0. B squared. When we had b squared, we had the number we needed right there. Let's see what they got. Check your answers. X squared over 9, y squared over 5 equals 1. That's exactly what we got. So you got to use that c squared equals a squared minus b squared and solve it for b. So don't make it harder than it is. It's not that bad. And it says if you want to put it in standard form, then you do that completing the square again. Find the vertices, and it shows you how to do that. Test your skills below. Find the center, vertices, and foci of this ellipse. All right, so you can take this and complete the square and come up with the equation like we want to see it, like this, where you can find the HK and that stuff. Let's see. Find this. So those are both completely squares. So they have one, and they check your answers. So I'll let you do that on paper, practice. There's completing the square, right? So it adds 4 there. It adds 1 there after it factors out of 9. But once it gets the equation, now you know everything you need to know. Again, I'll let you go through that. There's 2 of those for your practice. One more thing to add to our vocabulary. Eccentricity. Eccentricity. It's a measurement of the ovalness. How close to an oval is it? Interesting. It's the ratio E equals C over A. So the eccentricity is E equals C over A. I wrote that down in my notes. E equals C over A. C is the distance from the center to a focus, and A is the distance from the center to a vertex. So in a flatter ellipse, that ratio of C divided by A becomes closer to 1. Because the foci are close to the center of an ellipse, it's more circular. So if the foci is closer to the center, it gets closer to 0. So the closer to 1 that ratio is, the skiddier. It'll be stretched out further, right? And the closer it is to 0, the closer it is to looking more like a circle. So we actually have a little equation just to figure it out. If you know A and C, you can figure out, is this going to be close to a circle, or is it going to be closer to a really stretched out oval there? So, all right. The section on eccentricity in the online text gives the eccentricity value for 9 planets. Oh, interesting. We don't have the online text. You'd have to look that up. But which planet has the most oval orbit? Does it have all that? Check your answer. Okay, it didn't give us all of that. But in the online text, it gives you something. So you can't really do this section. All right, again, we have a table. Ellipse with center HK. All right, so here's the center. If the major axis is parallel to the x-axis, that means it's a horizontal ellipse. If it's parallel to the y-axis, it's an up and down ellipse. You can find the foci by taking H, because you know what the center is, add C to it, and that's where the foci point is. And the other foci point is at H minus the C, right? Because from the center, the focal point would be add the distance of C and subtract the distance of C. For a parallel one, when it's up and down, you add it and subtract it from the K instead of the H. The vertices, you add that distance of A and subtract the distance A. You do it from the H for the horizontal or from the K on the vertical. And then there's the equations again. A is always greater than B because it's the number of the major axis to the center, the vertices. So this is a nice summary for your notes. You can put all that table in your notes. Use that on the test. Remember, you can use all your notes on the test. It's just hard to go back and look at this lesson during the test because you have to close the test to come back to look at this lesson. That's why I say put it in your notes, and you can use this in your notes. All right, let's look at the lesson that goes with this. What do they ask us to find? Find the center, the vertices, and the foci when they give you this equation. So there's a squared and b squared. You can find c squared if you have a squared and b squared to find where the foci will be. Here's an equation, 2x squared plus 6y squared equals 12. So you're going to have to rearrange that equation because you need it to be equal to 1. So just take that equation and divide it by 12. 2x squared divided by 12, 6y squared divided by 12. Simplify, and that will give you your a squared, b squared. Which of those is it? Let's see. Graph the ellipse with this equation. A squared is 9, b squared 16. That should tell you whether it's up and down or left and right, right? And also should tell you what the center is because you got x squared and y squared. So which of these 4 graphs would that be? Oh, that's not too hard. That's not too hard. Because you know A and B, which one's bigger. That tells you whether it's horizontal or up and down. And you can see H and K is 0. Find an equation in standard form for an ellipse with a vertical major axis. Vertical major axis, it's an up and down ellipse. Length 6, minor axis, length 4. Which equation matches that? And let's see, an ellipse riding path is to be built on a rectangular piece of property. Here's the measurements, 10 by 8 of that rectangular piece of property. Find the equation if the path is to touch the center of the property line all 4 sides. So you know it's exactly 8 miles, the left to the right, and 10 from top to bottom. So it gives you the dimensions. Find the equation. That's it, 5 problems. All right, with your notes and the things we looked at today, this isn't that bad. I know you haven't done equations like this for parabolas and ellipses before, but just another way of looking at it and getting into the real math of how these things actually work. See, there's an actual math to an ellipse. It's the sum of those distances from the 2 foci to every point on there. Pretty wild. Probably haven't thought of an ellipse in that way before. So, all right, guys, that's enough. That's plenty. Hope you enjoyed your snow day yesterday. But now we've got all this fun ellipse stuff to do today. I know you wish you'd have known all this yesterday. You could have played with ellipses all afternoon. But that's all right. There's always a today or tomorrow or Thursday. But all right, if you got any questions, this is not an A day. This is a B day. Let me change that real quick. Tomorrow is the only A day you'll have this week. We have 3 B days this week. So if you need help, I'll be here Thursday and Friday. If your grade's below 70%, I'll see you Thursday and Friday. All right, guys. Have a great day.